Good morning and good afternoon, everybody. Thank you for joining our LinkedIn Live webinar today between Exebenus and Wintershall Dea. We'll just wait a couple of seconds for a few more of our attendees to join, and then we shall kick off and get started. While we're waiting for the final set of attendees, let me just introduce ourselves first. So my name is Tim Robinson. I am a senior data scientist at Exebenus. I am primarily involved with research and development as well as some product development. So we'll be talking about our product's usage today for stuck pipe risk detection in the Gulf of Mexico. I'm very pleased to have with me today Thomas Jaritz from Wintershall Dea, who is a senior drilling engineer there, who was the subject matter expert on this particular project, this exploration well campaign in the Gulf of Mexico. All right, so I think we're good to kick off now. So I will now start the session. Okay, so firstly, I'd like to begin with just a quick refresher on why we are interested in monitoring for stuck pipe risks during drilling operations at all. So the main reason for this is that stuck pipes are, as many of you are, I'm sure, are aware, a major source of cost and in terms of the non-productive time associated with them for the oil and gas industry. So this problem is fair to call a critical drilling problem, and I would estimate it costs the industry in excess of billions of dollars per year. There are some papers from I think it was from the 90s or the late 80s, where they had estimated the cost of stuck pipe industry in the kind of $500 million a year, and if you were to inflation adjust it, but I think that's a large underestimate of the problem. So from our best estimates, this is something which will hit the billions of US dollars annually. So the key issue here is that stuck pipe can really happen in any operation during the drilling process, and the non-productive time from this can range from many hours to many weeks in the most severe cases. And of course, the longer there is downtime, the greater the cost that is incurred. Now, this is particularly a problem when you are talking about high-cost offshore operations, especially ultra-deep water and deep water drilling operations. So in the most severe cases, it might be required that sidetracks are drilled, or even in the absolute worst cases, the abandonment of the wells. So all of this contributes to this very large dollar figure associated with this non-productive time per year. So just a quick breakdown here as well is that stuck pipe can occur just over half the time during tripping and reaming operations, according to this paper that we have linked at the bottom as a reference. And it can also happen while the drill string is stationary. This is particularly relevant for differential sticking. And roughly 14% of the stuck pipe events in the study were occurring during operations. So there's really a broad spread of types of operations in which this problem can happen. So during operations, we need to be vigilant at basically all times. Okay, so a quick note. I mentioned before we are going to be talking about the use of a stuck pipe risk detection and monitoring system that works in real time on some exploration wells in the Gulf of Mexico, which were drilled by Wintershall Dea. So just a quick intro to what the risk detection system was. And this is really based drawing upon some previous publications that we have done about the system, which are listed in the table on the right-hand side. But broadly speaking, we have multiple subsystems which are just concurrently monitoring for different types of stuck pipe risk symptoms, and they generate warnings based on these once those particular symptoms are detected. And each of these subsystems I would rather say a subset of these subsystems have machine learning models in them, which will be pre-trained for out-of-the-box usage. So that means you don't need to tune the system according to a new field or a new well, wherever it is. And this is something which is necessary for usage in an exploration well, because there may not be any offset well data available for the place where you're drilling. And that was the case with the exploration wells that Thomas will discuss in more detail over the next few slides. So one thing that's interesting to note is that when you have different combinations of symptoms which are identified by the risk detection system, these can give you some information about the possible mechanism that's actually causing the stuck pipe. An example of that might be if you have restricted motion, whether that be in an axial linear direction or rotational, but no flow restrictions, so you don't have any pressure spikes associated with increases in flow and that kind of thing, then it's likely that the mechanism behind the stuck pipe is a differential sticking risk. So the system has basically 3 broad subsystems, which will have then some different types of alerts that can be generated underneath those. So there's differential sticking, mechanical sticking, and hole cleaning as part of this stuck pipe risk detection system. And this is because these are the most common causes of stuck pipe that we see in the industry. Okay, so you might wonder why use a software-based monitoring system at all. And one of the key things to note here is that when you have software that runs automatically, this actually frees up the monitoring engineer's time from focusing on actually detecting every possible risk symptom to thinking about what sort of actions they should take to actually solve the problem. So imagine a case where you're monitoring several wells in parallel. You need to look for symptoms in each of these wells, and you could be doing 4 different wells as a monitoring engineer. So it becomes very difficult to maintain a consistent standard of hazard detection when your attention is being fragmented across the different wells, even if that one person could do an excellent job catching every possible symptom if they were focused on a particular well. It's just very difficult to do for humans. Multitasking, I certainly am not particularly good at it, and I don't think I'm the only one. So if you outsource this risk detection part of the process for a monitoring engineer to a automated machine learning or artificial intelligence based system, this helps to cut the cognitive load on the monitoring engineering teams and gives them space to actually use their human expertise to solve the problems. An extension of this idea is even within a single well, as I mentioned earlier, there are actually many types of risk symptoms that might indicate that you have a stuck pipe problem going on at that time, or potentially in the near future if those symptoms are leading indicators. So if you imagine in one well, we're looking at the multiple risk factors that could relate to a stuck pipe. This can involve looking for unexpected changes in hook load, torque, the rotary speed. Drops in rotary speed could indicate stalling, for example, pressure spikes, increases in ECD. You're building a picture up now of there being lots of different things that you have to look for simultaneously in order to identify the stuck pipe. Any one of these things could be quite easily found by a human, but spotting all of these different symptoms at the same time as monitoring multiple wells is a difficult challenge. And the software systems actually help with this. So they can do that kind of attention intensive part of flagging the risks and giving some indication of what the issue might be. And then the monitoring specialist can then focus on mitigation, as I mentioned before. In this case, interpreting the different symptoms that they see and then deciding on the actions to be taken. Okay, so with that, I'm going to pass over to Thomas to talk about the operational elements of this campaign in the Gulf of Mexico on these exploration wells.
All right, thank you, Tim. So jumping to the operational aspects, as I already mentioned before, we were drilling 2 wildcat exploration wells, actually the first wells in Mexico for Wintershall Dea. So we had limited or actually no offset data. And as already mentioned by Tim before, for us it was very important that we use a software which doesn't need to be pre-trained with data as they were just not available from our side. And this was the big benefit for a spotter for us on exploration wells. We didn't need to pre-train it. We didn't have any data. It was just for us more or less a plug and play solution. I can only talk about the engineering side. For me, it was very easy. We had 1-2 meetings to set up everything, to get to know the software and how the output looks like. At the end, I think our IT department had also 1-2 meetings just to set up the protocol, how we share our WITSML real-time data with Exebenus and how we get the output back. But if you look at the right side of the slide at the sketch at the bottom left of the triangle, here you can see the rig side, just to illustrate how the setup was. So you have the rig side. Obviously here in the rig, we generate our real-time data, which WITSML data as on all the other wells. and they are sent then to our remote data store. From there, Exebenus receives the inputs, our real-time data, and we receive them back the output from the spotter software, which then gets displayed for us at Wintershall Dea at Kongsberg. We use Kongsberg as a real-time monitoring software. And then on Kongsberg, you have a time-based graph, and you see all the 3 agents, which I will show you on the next slide. For us, we didn't have a real-time monitoring center in general, so we had a protocol how we will use the output and the notifications. On our side, we decided that the mat logger on the rig will, because they monitor the real-time data 24/7, will look at the different modules and then notify the supervisor in case a warning or alarm happens. An improvement there would be to have a real-time monitoring center, which then, of course, call the rig or the superintendent, depending on your protocol, if warnings or alarms happens. As a supervisor or me as a drilling engineer, we are not looking 24/7, obviously, only on the Kongsberg screen. Jumping to the next slide, thank you, team. Here's the post-well geological column of the first well. The first well was the well who took us longer, was more difficult. It was the main bore was an S-shaped trajectory. We also drilled a sidetrack afterwards as a success case. You can see that we drilled the Pleistocene, also the Upper Miocene, all the way to the MMU, which is the mid-Miocene unconformity. So we just hit the middle Miocene, but didn't drill into it. The casing design for this well was fairly conservative, a normal casing design, as we didn't know what to expect. So we had 2 contingency liners planned in this well. It was an 11¾ liner and a 758, which we both needed during drilling. So at the end, we ended up with a 6.5-inch open hole at well TD, and then drilled using a whipstock in a 958-inch casing and 8.5-inch open hole sidetrack. For all these sections, open hole, and for the casings, conductor, and so on, Exebenus spotter software was online. Could you go to the next slide, please? Here you can see the second well. In terms of drilling, was an easier well to drill. It was a J-shaped design, so not an S-shaped design. The water depth was 98 meters, so both wells were drilled with a checkup. Surface BOP. Casing design, again, we used the same philosophy, conservative casing design, and we drilled the well all the way to a 12.25-inch open hole section, only in the Pleistocene geology. And again, spotter was online for all these sections, starting from 36-inch to 12.25. Next slide, please. So jumping now to the results, what we received from the software in our Kongsberg system. First of all, on the left-hand side, you can see the first well was drilled 162 days. The system uptime was 99%, and also the Witzheim server uptime was 98%. Maybe the most important is the next one, is the false warning. This, of course, you want to keep as low as possible. For us as a client or using the spotter system, false warning would probably lead us to measures in case we think there is a stuck pipe event coming up, doing some, for example, reaming or tripping out of hole, which would be unnecessary, and of course, which end up in time and cost. So you want to keep these warnings as low as possible, which were there. We only had 24 false warnings. So, but as a client, you don't adjust the software itself. So this is done by Exebenus. They adjust the sensitivity to don't get too many false warnings, or as little as possible, but also keep the system as sensitive as possible to flag all the risks. On the right side, so I would like to show you one of our risks or nearly stuck pipe events we got. We didn't end up in a stuck pipe event, but this operation, we were just running the 20-inch casing, cementing the 20-inch casing and running in hole the 17.5-inch BHA to drill out the shoe. This is actually also the screen you see, which we saw on Kongsberg. So it's a time-based screen. You see on the first line, you have whatever we would like to display. We had the block position, standby pressure, flow in, torque, and so on, to just see which kind of operation is ongoing at the moment. And below you have the three modules: the differential sticking, the mechanical sticking, and the hole cleaning module, which gives you then the warnings or alarms. So warnings will be displayed in yellow, and then alarm will be displayed in red. If you see a green line, it tells you that the software is getting all the data and sends you back the output. So everything is fine and up and running. In this event, as said, we were drilling out the shoe, the cement in the shoe track, and at the bottom, at the hole cleaning agent, you can see two yellow warnings: fluid friction risk observed. So we saw this risk coming up. So we saw this fluid friction risk observed. So this could mean we might be drilling the shoe track too fast. We had a lot of cement blocky cuttings around the BHA, which could end up in a stuck pipe event. And if you look at the top, at the first line, you can see that we stopped drilling. We were reciprocating the string for, I think it was 20-30 minutes, to get the cuttings above the BHA, and then continued drilling the shoe track. And then at the end, when we were circulating while drilling and we had one bottoms up from these warnings, we also saw large cement cuttings at the shakers, which also confirmed on visually that the system flagged this risk properly, and we did the right measures to stop drilling out the shoe track, reciprocating, get the cuttings above, and we didn't end up in a stuck pipe event. Tim, could you go to the next one? So now looking at our second well, this well was drilled in 66 days. Again, the uptime was 100% on this well. Also, the width ML data were flowing all the time, 99%. And we had an average false warning per day of 0.27. In total, 18 false warnings during drilling the well. On the right side, you can now see again the output we received during drilling. So at these operations, we had already the 20-inch casing in place, drilled out the shoe track, and drilled a 17.5-inch section. In the open hole section, at one point, we had to pull out a hole and run back in hole with the drilling BHA. You can see here on the top, at the block position, what you can see in the screenshot is we started at 2017 meter, and then we went all the way down to 2,193 meters. At this point, at the mechanical sticking agent, you can see we got 3 warnings of overpull and taking weight. So at this moment, when we got these warnings, we put away actually the stand, stopped running and hold the BHA, and pulled out of hole the last stand and reamed up and down to get rid of this tight spot, which was detected by spotter. By doing so, afterwards, we didn't get any warnings anymore. We ran back in the stand, connected the next stand, and went back all the way to bottom, and were able to continue drilling without ending up in a stuck pipe event. These were the 2 operational events I would like to share. On the next slide, Tim, I would like to hand back to you, as you would like to speak about the updated version, I believe.
Yes, thank you very much, Thomas. So what we could actually see in that second well, I'll just point it back out on the previous slide, is that here there were certain symptoms which were observed relating to stuck pipes, which were not in scope of the detection system during these operations, which was back in 2022, I believe. So after the pilot period was on these exploration well campaign was completed, we then retested this well data using a modified version of the software, which basically just introduced a couple new risk detection systems based on pressure spikes and torque spikes, which was just in development at the time of this project, and so wasn't in the version that was used. So what you can see here is that the recall was a bit lower in this area and the precision was a bit lower because the particular symptoms that were relevant on this well just were out of scope. So what you can see is that when we introduced the new torque and pressure risk detectors, this recall went back up to 1. So all of the risks were detected through the retrospective analysis using an updated version of the software. So I'm just going to talk a little bit further about what happened with those. So what you can see here is during the original campaign, there was a period where there was a whole cleaning issue starting to happen and several pressure spikes, short-term pressure spikes started to emerge during the operations. And as I mentioned, these were just not within scope of the older version of the software system. So what you can see with the updated software is, which included this pressure and also torque detector, is that when you get these same pressure spikes, these are exactly the same time intervals, you can see that there were various pressure increase warnings being flagged along the way here. And yeah, the pack-off problems that ended up occurring a little bit later were, in the retrospective analysis, forewarned through these warnings. So there's a similar example as well, which we can share relating to the torque detection system that was introduced. Here you can see that in the original software version, although there were warnings raised ahead of the point where they got stuck, we can also see that there are additional confirmations of that mechanical restriction that come from analyzing the torque behavior. So around the stuck point here, there are some very large spikes in torque while operating with stable RPMs, and in some cases where the RPM would fall a little bit. And again, as the pipe started getting increasingly stuck, we saw lots of these torque risk alerts being raised throughout this interval based on the erratic torque behavior that was present here. So although in this case there were warnings being flagged ahead of the point where they got stuck, it's usually helpful to be able to use secondary confirmations on symptoms relating to the stuck pipe incident that's happening. As I mentioned earlier on, the combination of warnings that you see tell you something about the issue. So in this case, if you have mechanical restriction in axial direction, as well as resistance to rotation, that tells you something that there's a kind of a mechanical sticking issue going on, at the very least, in the area of question. Okay, so to conclude, what we have shown in our talk today is that the stuck pipe risk detection system we're working with, Exebenus Spotter, can be operated out of the box, and this supports the use of the system on exploration wells without any need for pre-training the system on offset well data. And in this case, that wouldn't have been an option anyway, so it was essential. So I'm just going to pass back to Thomas now to discuss the operational summary. Thank you.
Thank you, Tim. So for us, obviously, the most important was to keep the minimum false warnings about as low as possible, which was, in our perspective, achieved. And the major learning of this pilot for us was the communication protocol and how you set it up. So again, the Spotter software is an out-of-the-box plug-and-play solution for us as a client. However, to use the full potential of the software, it's very important to have a real-time monitoring center. If you don't have a real-time monitoring center, it would be good to have someone back-to-back, maybe in 12-hour shifts, to have someone looking at the output. For us, drilling our first wells, as said, in Mexico, we didn't have a real-time monitoring center for the 2 wet exploration wells. But again, this is the main finding for us, how I would use it in the future with a real-time monitoring center. Apart from that, it was very useful to use. We got a lot of good warnings and alerts, and it helped us a lot to not run into stuck pipe events, as you have seen before. At the end, we had 1 stuck pipe event in the second well. That was the stuck document we had. All right.
Thanks very much, Thomas. Much appreciated. Yeah, and the final note I'll just add is relating to those updates to the software that we discussed towards the end of the campaign. When you have this is just a really design point that's quite interesting. If you have a modular design, it's very easy to bolt on new forms of risk detection systems, and that was exactly what we found to be the case here. So there was a certain type, a very specific sort of symptom that was manifested in these wells that wasn't within scope of the version used. And then by integrating these new modules very quickly, you can start to consistently detect these and then make use of those during the operations. Okay, so with that, we would like to thank the Wintershall Dea Business Unit Mexico for all of their collaboration on this work, as well as our Exebenus colleagues for, again, their collaboration and all the support. Just like to mention that the work that we presented here today was based on a paper that Thomas and I and our other co-authors listed below here presented in March at the SPE IEDC International Drilling Conference. So with that, we will open up the floor for any questions that are coming from the audience. So I'll just quickly look for these. Just bear with me for a second, please. All right. So we have a question saying, did you sync the results back to the rig server for visualization? Thomas, I think perhaps that's best for you.
Yes, we did. So our setup, as said, we didn't have a real-time monitoring center, but obviously we were visualizing the Kongsberg output of the spotter software on the rig. We have dedicated screens in the company man's office, on the contractors' offices, and we also had them in our office for the engineering team, for myself and the rig manager, and so on. We had them in the offices, and that's how we monitored them. In addition, the MAT logger was actually the main focal point for us at this point. So in the MAT logging unit, we had one dedicated screen with the output of spotter. And the protocol was that if we get a warning or an alarm, the MAT logger will notify the rig supervisor, so our company man.
Thanks very much, Thomas. So we have another question for you. How did the on-site rig team accept the alerts? What was the decision protocol?
The on-site rig team. So yeah, as said, the MAT logger always was notifying the supervisor, and for the supervisor, more like internal in Wintershall Dea, we had a protocol. So we actually made a flow chart together with Exebenus, how to follow up on warnings and alarms. So obviously it depends on which model gives you a warning. If you get 2 warnings or if you right away get an alarm, how to go along the flow chart and what to do. But usually the supervisor was right away taking the actions itself and then informing the superintendent, and then the superintendent came to me and informed me. And then we were looking at the output as well and discussing the mitigation measures. But in general, hot shot, it was MAT logger informing the supervisor, and supervisor on the rig was, of course, capable to take the mitigation measures right away. And then in the meantime, he was informing the superintendent. So it was all done on site in the rig team. All right.
All right. Yeah, thanks very much. So with that, I think we're actually just out of time now. So thank you very much, everybody who has attended the session today. We really appreciate your time spent with us. And I'd also like to just reiterate a big thanks for Thomas for joining us today. It's great to have his expertise and a great guy to work with. So thanks again, Thomas. And with that, then we will close out the session. Thank you from me, and see you next time.
Thank you, Tim. It was a pleasure.